So continuing in Chapter 3, which was all about linear and quadratic functions, we're now going to go ahead and get into Section 3.3, quadratic functions. So far we did linear functions, their properties, linear models. Now let's learn about what are called quadratic functions and their properties. Okay, so by the end of this section, we should be able to graph a quadratic function using those transformations, the horizontal shifts, the vertical compressions, all of that stuff. Identify what are called the vertex and axis of symmetry of a parabola. Okay, remember, we have introduced this term before. Okay, the quadratic function is something that looks like y equals some kind of thing involving x squared. Something like, where is it? Maybe ax squared plus bx plus c. This is going to be a quadratic function. And we're going to plot it, and it should look something like this, a parabola. Okay. So can we figure out the graph? Okay. Can we find what are called the vertex, which is either the highest or lowest point? But I mean, I'm just briefly introducing this now. We'll get into it later. An axis of symmetry, so it might not be symmetric across the y-axis, but it will be symmetric across some other line. Can we find intercepts? If I know the vertex and something else, can we find what function it was, and how do I find where that vertex is? What is the highest or lowest point? Those are the overall objectives here. Okay, so as promised, here is the general form for a quadratic function, ax squared plus bx plus c. We also require a to not be 0. The reason why, if a was 0, we just wouldn't write it, in which case it would look more like this. And notice, what type of function is this? Bx plus c? This is exactly linear. So if a is 0, we would really have a linear function. Okay, so it's actually fine for b or c to be equal to 0. We would still call it quadratic as long as a isn't 0. Okay, what's the domain? It's all real numbers. There's no value of x that I can't square or multiply by something or add. So there's no domain restrictions here. So we've seen these before. The graphs all look like this. Okay. These are what we call upward opening parabolas. These correspond to when a is positive, and these have a minimum point. Here they're all graphed at the origin. Once we start doing horizontal moves and vertical moves, they could be somewhere else. But if a parabola opens upwards, it has a lowest point. Now, conversely, if a is negative, these are called downward opening. And they don't have a lowest point, they have a highest point. Okay, so if a is positive, it's an upward opening parabola and it has a minimum. If a is negative, it's downward opening and it has a maximum. And if a is 0, it's not even a parabola. Okay, so we can draw some conclusions. Okay, as a gets bigger, whether it gets bigger and bigger positive or bigger and bigger as a negative number, the graph opens faster and faster. Okay, and I'll go back to the previous page to see this picture. Okay, so here, for example, is a value of 3 compared to a value of 1 compared to a value of 1/2. If I was to do 1/10 x squared, it would open even slower. It would look something like this. And if I was to do something like y equals 1000 x squared, it would open up very, very, very quickly. It's tough to draw. But it would be a parabola and it would be very, very skinny. Okay, so as that number gets bigger, it gets skinnier and sharper. As the number in front gets closer to 0, it gets flatter. It opens up more slowly. Okay, so as that number gets bigger, it is vertically stretched. It becomes taller. As the number gets closer to 0, it's vertically compressed. It becomes shorter, or I would say it opens slower. As mentioned, if that number is positive, it opens upward. If that number is negative, it opens down. Okay. So no matter where it's drawn, okay, there's going to be a vertex. For positive values of a, the vertex is the lowest point, and then a vertical line through that point is the axis of symmetry. I do have a reflection across this line, which might not be the actual y-axis. It might be a different vertical line, but it is some sort of vertical line making an axis of symmetry. For a being positive, it opens up. Okay, we would say this is either upward opening or concave up. Use of the phrase concave up is predicting some calculus language. So if you want to get in the habit of using concave up to describe upward opening parabolas, that's fine. Okay, and therefore it has a minimum, which is the absolute minimum. It's never going to turn around and come back and get that low. Okay, it is the absolute global minimum of the graph. Conversely, if A is negative, the parabola opens down. It has a vertex, which is the global maximum. You can call this concave down instead of downward opening. Okay. Whether you're talking about concave up with a minimum or concave down with a maximum, that extreme point is called the vertex, and a line through that point will be the axis of symmetry. Okay. That's just like an overview of a bunch of terminology. Okay, come back for a second video where we will start going through these examples.